the University of Tokyo, where he earned his PhD in 1991. So he then moved to Lawrence Berkeley National Laboratory as a postdoctoral research fellow, and then a couple of years later he joined UC Berkeley as faculty, first as associate professor and then as full professor. Right? So he's widely known for major contributions in high-energy physics, astrophysics, cosmology that shaped the landscape of fundamental physics. So among his many distinctions, he was elected in 2013 APS Fellow. He is the founding director of the Kavli Institute for the Physics and Mathematics of the University of Tokyo, and he is currently the chair of the Particle Physics Project Prioritization Panel, right, which is a committee that sets the priority in particle physics research in the US for the next decade. So Hitoshi, welcome again to Brown, and we look forward for an exciting talk.
Thank you, Lucas. This is actually my first time at Brown University. Kind of surprising, but and I feel really home because I see so many familiar faces. Bob, I've known you for ages. Rick, Lucas, I just got to know. Greg, many people in the audience, so I'm very happy being here. And especially that when I started being the chair of this panel that maps out the U.S. particle physics program for the next 10 to 20 years, the first person that came to my mind who should be on that panel to think about what should be the future of the field was Meenakshi. And it came to a shock to everybody, of course, that when she passed away at the beginning of 2023, we were just supposed to start to work as a panel, hashing out the U.S. program for the next 10 to 20 years. And so I had to, of course, come up with a replacement with great sadness. And to replace her, it took 2 new committee members for that purpose. But anyway, so she was a real community leader. She was a shaker and mover, and she really cared about people and the health of the community. So, her loss was a big loss to me personally, and so I was very sad when we heard the news. I just wanted to mention that at the beginning of my talk today. So my talk today is kind of unusual talk for Colloquium, because I'd like to tell you a theoretical idea that's common to all of these things. Magnets on the fridge, cube of ice, fish of halibut, and rack of laundry. So what is the common theme among these 4 things from theoretical physics point of view? So that's the question I'd like to talk about today. And it all has to do with symmetry. And every one of us learned about symmetry as an important concept in physics, and that, of course, goes back to the famous theorem by M.E. Noether, that the symmetry is the reason we have conservation law. The energy conservation is not a principle. It is actually a consequence of the theorem when you assume that there's no origin of time. Then what you do experiment in the morning or evening shouldn't give you different answers. Once you make that assumption, energy has to be conserved as a consequence of the theorem. That's what we learn in undergraduate physics courses. At the same time, when you do have a conservation law, and when you actually do the quantum systems, and that conserved quantity ends up generating the symmetry, because the conserved quantity energy is a Hamiltonian, and in quantum mechanics, Hamiltonian is an operator that pushes time forward. So that's the idea of Noether's theorem. And indeed, we have learned over many centuries that laws of physics respect very high degrees of symmetry. For example, if you happen to see a spiral galaxy spiraling in one particular orientation, you're bound to find another galaxy spiraling in the opposite direction, because the laws of physics doesn't care left and right. Of course, there are some few exceptions like the weak interactions that do care left and right, but by and large, laws of physics is invariant, symmetric, interchanging left and right. If you also see an orientation galaxy like this one, you are bound to see all the other possible orientation galaxies too, because laws of physics is invariant under rotation. So symmetry of rotation is what gives you the conservation of angular momentum. And if you look at the distribution of galaxies in the whole universe today, so this is actually based on the data from Sloan's Sky Survey. You put in a galaxy as observed, a particular place in color and shape into the computer. You can sort of simulate the way you might do a space travel. And then you find that by and large, the universe is kind of boring. No matter how far you go, it looks pretty much the same. So that's the idea of translational symmetry of the laws of physics. Of course, if you want to really do this kind of space travel, you have to go at a speed which is 100 trillion times faster than the speed of light. So don't try this at home. But the idea here is that the universe seems to have this high degree of translational symmetry. So putting that together, we already talked about parity, switching left and right, rotation, and translation. And all of these things are actually the invariance of the Newton's laws of equations of motion. And so we know the laws of physics respect very high degrees of symmetry. And the fact that the laws of physics are symmetric means that you don't care if it's left or right. You don't care which way you're oriented. You don't care where you are in universe today. But then comes the question. So most of us are right-handed. And pretty much every one of you have your heart on the left-hand side of the body. So if the laws of physics are symmetric, what is the source of diversity we see in nature today? And that's the question. And at least part of the answer to this question is this idea called spontaneous symmetry breaking. So that's the idea I would like to talk about today, because that also had to do with a lot of my research I was doing over the last few decades. So to me, as somebody from Japan, the Yoichiro Nambu is one of the heroes, as a Nobel laureate, who actually brought in this idea called spontaneous symmetry breaking to particle physics. And the definition is a little technical. Suppose you have a system, physical system, that has a high degree of symmetry, which I call G. But if it happens that the ground state of that system respects only part of that symmetry, which I call H, then he predicted that there are multiple ground states that have exactly the same energies. They are degenerate. And you can count them up by looking at this coset space called G mod H. And in many cases, that would also lead to a prediction that you should have a massless particle or a gapless excitation to the system. So that is what Nambu told us. But to put it in more simpler terms, that's the idea where the rack of laundry comes into play. So when I do the laundry, and I try to avoid creating too many carbons, so I try to actually hang them on a rack and let them dry without putting it in the dryer. And when I hang the first shirt, it doesn't matter whether the shirt is facing left or right. I can do it either way. But when I hang the second shirt, I have the tendency to put the shirt facing the same way as the first one, just so that it looks kind of neat. And the third shirt, fourth shirt, and at the end of the work, I find, looking at the laundry and said, oh my goodness, why are all the shirts facing left? It doesn't have to be that way. One day, I might find all the shirts facing right, but at the end of the day, every time I do the laundry, I find myself hanging all the shirts facing one way over the other. It really doesn't have to be orienting in one particular direction. It could have done it either direction, but it ends up being that all the shirts are facing the same direction at the end of the day. So that's an example of the idea we call spontaneous symmetry breaking. So it's a symmetry that shirt can face left or right. It doesn't matter. But at the end of the day, the ground state of all the laundry, I end up finding, has all the shirts orienting one way, but not the other way. They end up choosing one particular direction. And so that's the idea called spontaneous symmetry breaking, because the symmetry is now broken once you are done hanging all the shirts. The same thing is what we see in halibut. And halibut is an example of what is called the flatfish, where both eyes are on one side of the body. And clearly, they did evolution in such a way so that they can actually lie flat on the ocean floor in the sand to hide from all the predators, that they wouldn't be eaten. They are protected that way. And in the course of evolution, they had to make a decision. Do I want to move both eyes to the left-hand side of the body or right-hand side of the body? It doesn't matter which way. But they had to choose one orientation so that they can be a flatfish and be protected on the ocean floor. And as a matter of fact, halibut has both sides on the left-hand side of the body, but flounder has both sides on the right-hand side of the body. Then I can prove that they are different species because I eat both of them, and they taste differently. Halibut has a very smooth taste and kind of clean taste. It's great for sushi. And flounder has a little earthy smell. It's still a great fish, so I tend to actually simmer in a sauce for a while. It's still very delicious. So they are different species. So each species chose one particular orientation over the other. So they had to break the symmetry spontaneously. Namely, it doesn't matter which way, but they have to choose one way over the other. And there are many examples of this in biology. So Professor Kuroda is a great biologist I happen to get to know, and she studied the idea called chirality in biology. So if you look at conch, that's a kind of shellfish where the shell winds around in one particular direction. The shell starts to actually wind around in one particular direction already at a time when the cells start to divide, they start to move in one orientation. What she did is to force these divided cells to start winding around in the opposite direction, basically by nudging them. So you see her nudging with a little glass tube on the left-hand side of this slide. And once she did that, and that cells ended up becoming a perfectly happy, healthy adult conch at the end of the day. So it's a simple enough biological organisms that it really doesn't have to be winding in one particular orientation. But of course, the direction is written into their DNA. So even though you have this adult conch which winds around the opposite direction, their children would end up winding around in a normal direction. But anyway, again, in the course of evolution, to produce this particular shape of the shell, they had to evolve in a way to choose one orientation over another. And that can actually lead to a money-making proposition for many of you. So if you look at the sugar molecules, they also have two different orientations. But it turns out that we can consume one orientation called D-glucose because we have an enzyme to break it down. But our enzyme cannot break down L-glucose, so we cannot digest it. And so it turns out that entire biomass on a planet can consume sugar of only one orientation, and all the plants also produce sugar of that orientation, none of the other ones. So this is the sort of the important proposition to you, especially young students. If you can come up with a manufacturing process that can mass produce the sugar with the opposite orientation, you can be an instant billionaire because that is going to taste the same chemical composition, but 0 calories. You can't digest it. So if you can come up with such an idea, remember, you heard it first from me, okay? And the same applies to also amino acids. There are two different orientations, but our entire biomass is made of only one orientation of amino acid. So this is where, again, you see an example of spontaneous symmetry breaking. And in fact, knowing that the amino acids comes in two different orientations can be useful because there has been this idea that maybe the life on our planet came on asteroids. And in fact, actually all the water which had leaked into the Rick's laboratory over the weekend, all the water in our planet actually have come from asteroid impact. When the Earth was formed, it was too hot for water to exist, so it came later and brought in by asteroid. So if that's the case, why not also life? And indeed, when the Japanese Space Agency, JAXA, sent a probe to one of the asteroids named Ryugu, and went there, took the sand, and came back, a sample return mission, the first thing they try to see if, first of all, are there any amino acids? Was there any life on this asteroid? And second, is the amino acid of one particular orientation over the other? Then it turned out that it was 50-50. So that is taken as a sign that it's not as a result of life on the asteroid, but just random synthesis of molecules. That's why it's 50-50. If there was actually the active life forms on the asteroid, they would probably have also chosen one orientation over the other. So knowing that simple fact already tells you something. So in all of these examples, being physicists, you would like to write down an equation of some sort, and that is all described by this simple shape of the potential energy. So this potential energy is invariant in flipping the sign of x to minus x, because it's an even function of x. And as a result, you have two minima for the potential, one on the right, one on the left. And because they are related by the symmetry, they have exactly the same energy. So system can choose either one of the minima, but if you are Halibut, you have chosen one. If you're Conch, you also have chosen another. So you have to choose one out of many possibilities, and that's the idea of spontaneous symmetry breaking. So here I'm talking about the symmetry of the inversion between left and right. That's one example of what is called discrete symmetry, because there's only one operation you can do and nothing more. But in other cases, you can also have a continuous symmetry called rotational symmetry, for example. And this is actually a picture I got from the one write-up by Nobel Foundation when they talked about this idea of spontaneous symmetry breaking. And this is the way how they try to explain it. So if we have a pencil standing upside down on a sheet of on table, and I'm trying to move cursor over there, and if you manage to actually let the pencil stand upside down and completely vertically up, then the pencil has a symmetry of rotation around it. And what Newton's equation of motion tells you is that it would stay that way. And that, of course, sounds crazy. Just a little dent or maybe a weak wind would eventually let the pencil fall down in one orientation over the others. So when the pencil falls, it picks one particular orientation, not the other ones. Again, it could have fallen down in every possible direction, but it has to choose one when it hits the table, namely that's the ground state of the system. So rotational symmetry is now lost once the pencil falls on the table. They also use another example. Suppose you have a rod standing straight up, and if you try to press it down, and up to some point, the rod would resist your force, but beyond some point, it would buckle. And when it buckles, it can buckle towards you, it can buckle towards the door, it can buckle towards me, it can buckle in any possible direction, but it finds one particular direction to buckle. So once again, when you get to the stage, the system has chosen one orientation over the others, so the rotational symmetry is spontaneously broken. That's where the magnet on the fridge comes in. So the idea of the magnet is that it's made of large number of electrons. Each electron has a spin, and as electron with spin, of course, has a magnetic moment. So each electron is a little tiny magnet on its own. So when you have a molten iron piece of steel at high temperatures, all the electrons are oriented in random direction. But once you start to cool them down, at some point, each spin wants to be parallel to each other. They want to line up. And at the end of the day, you find all the electron spins lined up in one particular direction. Then you find that they form a magnet. So that's the ground state of all the electrons, and that forms a magnet. And when you are just gradually cooling down the system, the spins can orient in one direction or another direction. And it doesn't matter which way, because the Hamiltonian of a system is invariant under rotation in all directions. But ground state ends up finding one particular direction over the other. And when you go back to higher temperature, the spins start to fluctuate, and eventually you lose any particular orientation. But at the low temperatures at the ground state, they all point in one particular direction. And this happens, again, in many, many different systems. And that's where the cube of ice comes in when something is frozen. So I'm not talking about this frozen here today. But when you start with the hot gas of water vapor, and the vapor is, of course, gas, where water molecules are moving all in random directions. So there's no particular place in the gas. There's no particular orientation in the gas. So this stage of water is invariant under translation and rotation. But once you cool the system down so that it would freeze into cubes of ice, that's no longer true, because cubes of ice is made of lattice of water molecules. So they are sitting on one particular point in space, and they also have a particular orientation. So rotation and the translation are now broken when the water freezes into cubes of ice. And there are many other examples which look a little bit more abstract. For example, if you cool a system of helium-4, which Bob is the world specialist of, then you find they've become a superfluid so that they lose viscosity.
Ordinarily, this container with tiny pores can hold liquid helium.
You could this liquid helium
But the moment the
down to
helium
temperature,
turns
when
superfluid, it leaks through.
and starts dripping from the bottom of the
We call this
speaker,
kind of
which is
flow
porous,
a
has
superflow.
tiny holes in it, because it becomes totally
Superfluid helium can
namely
do
a fluid
things
with no viscosity. And that is actually caused by the fact that the macroscopic wave function of helium can change its phase, that is the symmetry, but this symmetry is broken because the wave function ends up choosing a particular phase throughout the system. And the symmetry of changing the phase of the wave function is what leads to the conservation law of number of atoms in the system. But conservation of number in this case is actually lost. And that's how the whole system can be described by a macroscopic wave function on one particular phase. And if you go to a superconductor instead of superfluid, you can even change the phase arbitrarily from one place to another. That's an idea called gauge symmetry. And in a piece of superconductor, this symmetry is broken, and that's why a piece of metal or even some ceramic can lose resistivity for the electrical current. And that's what you might do in undergrad laboratory with the Meissner effect. And that Meissner effect is the reason why we can now start building these magnetic levitation trains, where entire train is lifted up by the force of magnetic field. And to have that strong magnetic field, you have to have a high current. And in order to have a high current without any loss in energy, you need to use superconductor. And that's how this kind of technology becomes possible. So all of these examples, once again, can be all described with one simple equation. So instead of this potential, we take this potential and rotate it around and make it three-dimensional like this one, so that potential has a symmetry of rotation around this axis. So this potential is axially symmetric. But when you look at this potential, suppose you imagine you place a ball at the top of this tip, then it will start falling down one way or another, and eventually find yourself to be sitting at the bottom of this potential, but this potential has the same energy throughout this circle because they are all related by the symmetry of axial rotation. And you can write the form of the potential this way. So if you have x and y axis, and x squared per y squared is invariant under rotation of this plane, and you see the bottom of this potential is always when x plus y squared is 1, which means there's a circle at the bottom. And anywhere along this circle, energy is 0, and therefore it's the ground state. So this kind of example happens a lot in physics. And it turns out in particle physics, we have been actually struggling to understand the nature of a force called the weak interaction, or weak force, that is responsible for causing the nuclear beta decay. And the problem is that we learned about the nature of this force by using very high energy accelerator experiment called LEP that used to sit in the same tunnel where the LHC experiment is now being done, and many people in the department are working on it. And from this experiment, we learned that the nature of the weak interaction is very much the same as electromagnetism we learned in Jackson. Jackson actually was a professor in Berkeley too, so he was very helpful. Whenever I traveled, I always gave him my lecture note and asked him to do a substitute lecture on quantum mechanics. And he was also a very serious person. So when I came back from the trip, he always handed me my lecture note back to me with a lot of red ink on it. Anyway, but so what we learned is the weak interaction is very much the same thing as electromagnetism, but there's one major difference between them. We know electromagnetism is a long-range force. That's why if you have a compass in your hand, the needle gets pulled by the North Pole of this planet, goes over a long distance. But weak interaction doesn't even go over the size of an atom or even a nucleus. it goes over only 10 to the minus 16 centimeters. So how come the same kind of forces, one of them is long-ranged, another one is so incredibly short-ranged? And that's where we actually had to learn from our condensed matter friends, namely that superconductor does the same thing. So superconductor actually repels the magnetic field, and magnetic field can actually get into this, but only by a little bit, of maybe 100 microns or so. So magnetic force is a short-ranged force in a piece of superconductor, we learned. So that actually gave us an idea. Maybe we live in a superconductor. The entire universe is a piece of superconductor. So something is filling up the universe, just like the pair of electrons in superconductor, that actually bothers these weak interaction forces so that it has become a short-range force, even though it is supposed to be the same kind as electromagnetism. So that led to the idea is that our universe has so many particles stuck in it, and that particle is what is called the Higgs boson. And when light travels through space, the light photon is known to interact with anything that has electric charge, but Higgs boson is electroneutral, so light doesn't notice that there's a whole bunch of Higgs boson in empty space today. So it's actually not empty, and just keeps going at the speed of light. But when the weak force wants to act on a distant body, while it wants to go, it gets disturbed by this Higgs boson everywhere around it, gets bounced around, and ends up not going very far. And that's how the weak force, we believe, has become such a short-range force. And for other particles, like even electron in a body, it doesn't interact very much with the Higgs boson, but still gets disturbed. So even though electron wants to go with the speed of light, it can't get slowed down, and that's how electrons can happily go about in atoms around the nuclei. So that's the idea. So Higgs boson fills up the entire universe. And in fact, it needs to actually fill up the universe with exactly the just right amount. If you have too many of them, weak interaction really doesn't go anywhere, then the sun wouldn't burn, and you wouldn't be able to live in that kind of universe. If the Higgs boson are too few, then weak interaction can go the long way, then the whole universe becomes too radioactive for us to live. Somehow, the Higgs boson has chosen the exact right amount to be stuck in the universe today so that we can live happily in the universe. So if the Higgs boson is frozen in the universe today, and suppose just imagine that it evaporates for some reason right now, then all the electrons inside the atoms would start going the speed of light, and atoms would disappear. So that's what happens here. Now, never mind that I'm so old, I have a picture with Einstein shaking hands, and it's even a full-color picture. Don't ask why. But the point here is that both of our bodies would also evaporate in a nanosecond if Higgs boson disappears from universe today. So we are here in one piece thanks to the Higgs boson. So Higgs boson is filling up the entire space like a group of superheroes, protecting us from evaporating and maintain being in one single piece. So that's why a lot of people are spending time trying to understand this question even better. So why such a particle exists in nature? Why is this particle alone that got stuck in the universe today? So these things definitely have to do with the question, why do we exist at all? So that's why people have a lot of stake in trying to answer these questions. And of course, to produce Higgs boson on a Large Hadron Collider, we had to spend enormous amount of money and time and people to do so. So I'm always jealous of our friends in condensed matter physics. So right after the Higgs boson was discovered at the Large Hadron Collider, one of my friends at the University of Tokyo did the following experiment to whack a piece of superconductor with a terahertz laser in femtosecond pulse. So if you whack a piece of superconductor, what's going on is again the same potential, and you have chosen ground state somewhere at the bottom of this potential. But when you whack it a laser, your state can go uphill, and then starts to go swish, swash, swish, swash, and go back and forth in this potential. And that's the Higgs boson in the superconductor in laboratory. So he could really see this radiation coming out with a particular frequency. And that frequency is telling you the energy of the Higgs boson is in superconductor. So this experiment might have taken only a few $1 million to do so I'm jealous about that. But in all of these examples, there's one famous theorem which you can find in any books on quantum field theory, and that's due to Jeffrey Goldstone at MIT. So he said the following. So when a continuous symmetry is spontaneously broken, just like in superfluid helium or this rod, then there appear the same number of massless particles or gapless excitations, namely you can create excitation without putting a lot of energy into it, and the number of them is the same as the number of broken symmetries. And also, the energy of this excitation is linearly proportional to the momentum of the excitation, called linear dispersion. And this kind of degree of freedom is called Nambu Goldstone boson, thanks to these great people, the predecessors of us. And you see them. For example, when you collide a heavy ion nucleus, in this case lead, and when you actually accelerate them up to relativist speed and smash them against each other, the lead nucleus becomes a pancake because of Lorentz contraction. They hit each other, and at that point, it becomes so dense and hot that the nucleus starts to melt into a soup of quarks and gluons they are made of, and then starts to expand and turn back into some kind of objects, particles at the end of the day. And this is a picture of one such event. You produce so many particles, called pions in this case, because they are very light. And the reason why they are light, again, is due to this idea of being Nambu Goldstone boson based on a symmetry which is named chiral symmetry. And of course, this kind of system is very difficult to understand because of the strongly coupled nature. Showing the chiral symmetries is indeed broken in nature has been very difficult theoretically. So recently I came up with this idea of trying to show it on a single piece of paper. So it's very much similar to the idea of what happens in the cold atom systems. When you have a gas of fermions, that's Fermi gas, when you introduce slight attractive force among them, they might become BCS state, just like in superconductor. And if you keep making the attraction stronger and stronger, at some point, you'd rather talk about two fermions binding into bound state, becomes a boson, and boson condense, like in liquid helium-4, to cause boson condensate, and they are all continuously connected. So if you take this idea with an idea called supersymmetry, and you can actually solve these strongly coupled theories once you actually put supersymmetry in there, but it doesn't seem to resemble the real world at all. But the minute you put in a small breaking of supersymmetry on top of it, you can still solve it and show that theory actually does break chiral symmetry spontaneously, and hoping that that will continuously connect it to all the way to infinite size of SUSY breaking, that is the real world. At least you'll learn that chiral symmetry can be broken by the strong interaction theories. So that's an idea of basically what people call spherical cow. If you like to understand the real cow, that's always a difficult problem. So let's say you make the cow spherical. Then it doesn't look like the real world at all, but when you actually break it a little bit, you can start picking up all the features that mimics the real world of the strong interaction. And indeed, that is something you can show. So that's the way I'm making a little progress trying to understand what's going on there. And this idea not only works in particle physics and nuclear physics, it seems to work in condensed matter physics too. So when water freezes into ice, I told you that two translational symmetries are broken here. I can't draw 3 dimensions, so I'm just talking about 2 translations here. And when you have the translation symmetry broken, what you can do is you can whack the system using the translation. So if I use this translation up here and whack the system, then you can see the lattice starts to vibrate like this one. And that's a sound wave. Quantized version is called phonon. So in this case, what is called the longitudinal phonon. But you can use the other translation going sideways, and you whack the system with that, then you can have this shear mode of the sound waves, and that is what is called the transverse phonon. And in both cases, energy really does go linearly with momentum, according to Goldstone's theorem. And also for each symmetry that is broken, you generate these gapless excitations of the system. So the Goldstone theorem does seem to work. It also works with the superfluid helium-4. I told you already that what's broken here is the symmetry of changing phase of this macroscopic wave function. And if you do the neutron scattering, you can map out the elementary excitations in the system. And compared to usual p squared over 2m, that's the non-relativistic atoms, you see a spectrum that rises linearly at the small momenta. And not only superfluid helium-4, if you look at the system of the Bose-Einstein condensate of dilute gas of cold atoms at nanokelvin temperature, again, you see a linear relationship between momentum and energy for the small momenta region here. And this is actually done by the scattering light on the system. And once again, you see this idea that you have excitation, which goes to zero energy for zero momentum, and rises linearly with momentum, and one excitation per each symmetry that is broken. And it is believed the same thing is happening at the core of the exploded star that became neutron stars. So this also appears to have in many places. A neutron star becomes such a dense star, but after the supernova explosion, it's still spurting out the gas out of this core. And in fact, our body is made of the stuff that came out of this explosion of stars. So the idea seems to work pretty much everywhere until the moment when you go back to this example of the magnet on the fridge. So you all know the magnet can be described by this famous Heisenberg model, and you have electron spins, and they're coupled in this interaction in the nearest neighbor. And depending on the sign of this coefficient, you can either have antiferromagnet or ferromagnet. And the Hamiltonian has a symmetry of rotating all the spins together because it's a dot product of two vectors. And for the case of antiferromagnet, because of this positive sign, when spins are aligned, you have higher energy than when the spins are anti-aligned. So the ground state would look something like this. It's an approximate form, but nonetheless, it would look something like this. On the other hand, for the ferromagnet, when the spins are aligned, you can lower the energy, so the ground state would look something like that, or the spins are lined up in one particular direction. In both cases, the ground state is degenerate because the spins can orient in all directions. So possible set of vacua or ground state form a basically two-dimensional sphere, giving you a point that corresponds to one orientation of all the spins together. And in the case of antiferromagnet, you see that two rotation symmetries are broken. Because if the spins are lined up in up and down direction, rotating spin sideways is not a symmetry of the ground state anymore. That's broken. Rotating spins front and back, that's also a symmetry that's broken. But rotation around the axis is still a symmetry of the ground state. So out of three possible rotations, two of them are broken by the ground state. One of them is unbroken. So you would expect there are two gapless excitations in the system, and indeed, there are two gapless excitations. But in the case of ferromagnet, this has been known for a long time, there's actually only one gapless excitation. Something is wrong with the theorem. And in the case of antiferromagnet, once again look at the spectrum of the excitation, energy goes linear with the momentum. But for ferromagnet, it goes actually quadratic with momentum, not linear. Once again, something is wrong. So for ferromagnet, naively, you would have expected two gapless excitations because you can whack the system to rotate sideways, and that will give you this kind of excitation. Or whack the system to rotate it up in front, and then you would expect this kind of excitation. But it turns out that these two excitations don't exist. The only excitation that exists in ferromagnet is this kind of rotational motion where spins are going circular at each site, but not the other way around. There's only one excitation of this type where the energy goes quadratically with the momentum. And I didn't know much about these things, but it turned out that nuclear physics community started to look into many other examples where they talked about the Colloquium condensate, which may happen at the core of a neutron star. Eventually, we hope to learn about it using gravitational wave signature. But here the title says abnormal number of Nambu Goldstone bosons. Again, they seem to see fewer number of Goldstone bosons than the number of broken symmetries. once again, you see abnormal number of Goldstone bosons. Now back to condensed matter physics, this system is talking about some kind of spin order, but here again, talking about abnormal number of Nambu Goldstone bosons. So this start to become a bit of a problem or puzzle in the community. And even Nambu himself wrote a paper on this, and it's actually very interesting. So after reviewing this basic idea of spontaneous symmetry breaking, at the bottom he says, there are, however, exceptions to the above theorem, and then he talks about the anomalous property of Nambu Goldstone bosons. Once again, something is not normal. Something is going wrong. And what made me actually the happiest about this paper from Nambu is the fact that he was very modest guy, very humble. He never bragged about himself, and he never talked about what a great physicist he was. But in this paper, he referred to this as Nambu Goldstone boson. So he has some level of pride in it. So that made me very happy. But anyway, so I didn't know much about this stuff. But when I was teaching quantum field theory class in Berkeley, there was one student who raised his hand and said, "Professor, you're wrong." "What do you mean I'm wrong?" And of course, that was a question. And he knew some of these examples already and was thinking about it. And he was clear to him that it didn't seem to mesh with the theorem by Goldstone. Something is wrong. So then we tried to sit down together and talk through it. Okay, what is exactly the problem? And then I realized that I don't understand something. And we got to work together. And eventually, we came up with a new theorem that works on all these examples. So look at what difference between antiferromagnet, where Goldstone theorem seems to work, and ferromagnet, where it doesn't. The big difference is this. In the case of antiferromagnet, spins are staggered, so they cancel between two neighboring sites. So if you add them up, then there's no expectation value for the spin. But for ferromagnet, they all lie in the same direction. So if we add them up, you have a big expectation value of spin in z direction. And as you all learned in quantum mechanics class, spin in z direction can be written as a commutator or spin in x direction and y direction. So now you see the spin in x direction that rotates the system this way, and spin along y direction that rotates the system that way, actually don't commute, and it has a big value now. And that looks very much similar to the canonical commutation relation in quantum mechanics, that x and p don't commute. And what we know is that x and p together describe a 1 degree of freedom of motion, right? So when you're looking at motion in x direction, you need to specify the initial position and initial velocity in Newtonian mechanics. And of course, they become canonical conjugate in quantum mechanics. But the point here is that both x and p are referring to the same degree of freedom. So two operators end up describing 1 degree of freedom if they have this commutation relation non-zero. So it turns out what's happening in a ferromagnet is exactly the same thing. The spin in x direction and spin in y direction, we thought they were independent degrees of freedom, but now that their commutator is non-zero, they became canonically conjugate to each other, and together, two of them together describe a single degree of freedom. That actually turned out to be the idea. And when we wrote the paper, of course, we had to resort to the language of quantum field theory, but it turns out that the very first term you can write in the Lagrangian allows you to have this non-zero commutator. And when you have that term as the first term in the Lagrangian, then you see that it is a form of pq dot minus h, because there's only one power of time derivative in the Lagrangian. Then two things are conjugate to each other. So it turns out that two Nambu Goldstone fields end up describing a single degree of freedom because they are canonically conjugate to each other. And you can further show that this coefficient in front of this term really has to do with the commutator of symmetries. As a result, because two of them end up describing a single degree of freedom, whenever you have this commutator, you lose half of the number of the commutators in actual counting of degrees of freedom, So I have to subtract the half of that. And this formula is now the new theorem and seems to work everywhere. So here, a whole bunch of examples people talked about in the literature, but once you actually take this now correction of subtracting half of the number of commutators that are non-zero, then after subtraction, see, all of them seem to work out. So we became very happy about that. And we published in a Physical Review Letters, and it can be described by a piece of mathematics called presymplectic structure in homogeneous spaces. Never mind what the name is, but it actually works. And the most dramatic example we learned along this line is what is called spinor BEC. So this is yet another example of the boson condensate of cold atoms. But when the atomic physicists refer to spinors, here they mean like spin 3, not spin 1/2. And when you have this condensate, boson condensate of atoms with spins, then you also break symmetry. But because of the spin, let's say spin 1, then the spin 1 has 3 states, 2s plus 1, as we learn in quantum mechanics. And rotation among these three states is a symmetry. In addition to changing the phase we talked about before, so you have 4 symmetries now. 3-dimensional rotation, orientation of spins, and the phase of the wave function, you have 4 symmetries. But in one phase of the spinor BEC, you have this rather complicated pattern of expectation values. And it turns out that if you actually break it down to the real part and imaginary part, you can see that this pattern preserves combined rotation of phase, that's 2-dimensional rotation between 2 columns of real part and imaginary part, and also 2-dimensional rotation around the axis, and that symmetry is unbroken. So out of 4 symmetries we started out with, you end up having only 1 symmetry left. So you have broken 3 symmetries. But even though you have 3 broken symmetries, once again, we see only 2 Nambu-Goldstone bosons. You see fewer than the number of symmetries, and one of them has this linear relationship, but another one has the quadratic relationship between momentum and energy. And that's something we have seen in the case of ferromagnet already. So counting works again. In the case of this quadratic relationship, you have this commutator in action. So 2 broken symmetries describe 1 degree of freedom. For the linear one, it's standalone. So altogether, 3 symmetries end up giving you 2 excitations. Both of them are Nambu-Goldstone bosons, but one of them has a linear relationship, another one with quadratic relationship. So we begged my colleague Dan Stamperkern, who worked in Kettley's lab to produce this cold atom BECs, and to measure this quadratic relationship between energy and momentum. And lo and behold, he did find this quadratic relationship between energy and momentum. So everything works out in the end. So that's how we learn how these things work. Once you have a system which is not relativistic, but non-relativistic, so that you can have this non-zero commutator. And I don't get into this the geometric interpretation of this, but there's a well-founded foundation for this idea based on the presymplectic geometry on homogeneous spaces. And once you have a mathematical language to describe it, you can start classifying what are the possibilities that can be realized in principle. So no ambiguity anymore. You can list up what kind of pairing is possible between different symmetries and so on and so forth. And having understood this, that actually really allowed me to expand my horizon to think about how to use these systems. And again, for superfluid helium, but in this case helium-3, which is a fermion rather than a boson, which also becomes superfluid at a very low temperature. In one phase of superfluid, again, you have this complicated complex wave function. In this case, not only 3-dimensional, the 3 components along the column, you also have 3 rows. And you have this 3x3 matrix describing the superfluid. And now we know what kind of excitations are possible in this system. And that actually led to a proposal that if you would like to detect a kind of dark matter particle called axion, so superfluid helium-3 turns into ferromagnet in one phase, and if you apply a magnetic field, that also develops a gap. And it so happens that the kind of mass of axion dark matter people are talking about of order microelectron volt is something you can obtain as a gap in this ferromagnet in sort of typical 10 Tesla magnet. So then you can resonantly capture axion by this gap in the ferromagnet of superfluid helium-3, and it can, in principle, get down to the level of sensitivity as theoretically predicted if you manage to actually cool helium-3 down of 1 liter of helium-3 down to a millikelvin. And that kind of cryogenic system, I understand, is still very difficult to do. But if you know the axial mass already from some other experiments, you don't need that much volume because you don't need to scan. So at least it becomes a possible experiment once you know the basics about how symmetry breaking works. And so I've been doing research along this line of thinking in what other ways the symmetry breaking can be actually interesting and useful. And you know that dark matter has to exist in a universe. In fact, we wouldn't be here if there weren't for dark matter, because the gravity of dark matter is what assembled the gas to eventually become stars and galaxies, and we were born out of it. So whenever I give a public lecture about dark matter, I always tell people that I regard dark matter to be my mom because I was born out of it. So that's an important thing for us to understand. And people try to understand the distribution of dark matter in all kinds of different galaxies. And there are some specific set called dwarf galaxies, which are very dim and small and light. And some of them, the density profile of dark matter doesn't seem to quite match up with what people predicted theoretically. And there had been a speculation that maybe dark matter particles we think are very weakly interacting, with us at least, maybe actually strongly interacting among each other. And that impact of self-interaction among dark matter can change the distribution in a way that would actually explain the data. But for that purpose, it turns out that you need a fairly sizable cross-section for dark matter interacting with itself, which is given by basically the size of an atomic nucleus, like protons and neutrons. That means it's some form of strong interaction. So that prompted me to think about dark matter being possibly a composite object, like pion I talked about, or protons and neutrons that are made up of quarks and gluons. And then the dark matter would have a finite size because it's a bound state. Then they can hit each other and scatter, and that can actually explain the data of the dark matter distribution in dwarf galaxies. And once I actually started to talk about this, we came up with this idea that the dark matter may not be WIMP, weakly interacting massive particle. That has been the main paradigm for dark matter in a community for many decades. But once you think the dark matter is this composite object, which is yet another pion or Nambu Goldstone boson, you know exactly what kind of interaction can happen among each other. And one particular term, which is called topological, which also is subject of a Nobel Prize in condensed matter physics to Howden, Kostadis, and Taulas, this topological interaction can also give you this 5-point interaction. So the dark matter would freeze out from 3 to 2 annihilation process. Then you would predict a very different mass range compared to 300 GeV for WIMP. It should be 300 MeV, so 1,000 times lighter. And it's also strongly interacting instead of weakly interacting. And then you can actually start exploring this kind of behavior of dark matter. And one of the things I've been doing is working with a group of astronomers. We just finished building a new multi-object spectrograph for Subaru telescope that we can point 2,400 optical fibers to individual stars in the dwarf galaxy and measure their redshifts and therefore their velocities to map out the density profile of dark matter in this system better. It took me 15 years to finish this, so it took a long time, a lot of money and people, but nonetheless, it's a very complex instrument where you have this wide-field corrector system that already exists. You need to put in these fiber positioners to position each tip of the optical fiber within 10 micron accuracy, and you have to line them up into this the prime focus plane, and then put that into this instrument. There's not enough optical fiber before that way to prevent the stress, and so on and so forth. So we're hoping to get better data to understand this question even better. Now, final subject I'd like to talk about is really about why we exist. So what we learn in quantum field theory is that every particle is accompanied by its antiparticle counterpart. And when energy turns into matter, the matter and antimatter are always produced in pairs, 1 to 1. And these days, of course, the universe is so cold, we don't see that many antimatters around us. But at the time of the Big Bang, it was so hot, so much energy, and that energy turned into matter with the same number of antimatter. That's what we know as the laws of physics today. But if it stayed this way, as the universe expanded and cooled, eventually matter and antimatter would meet each other, and it would annihilate back into energy 1 to 1, and the universe would have been completely empty, so you wouldn't be here today listening to me. So something must have happened from the time of the Big Bang, when same number of matter and antimatter got created, that actually shifted the balance towards matter by picking 1 out of a billion antimatter and turning that into matter somehow. And only if that happened, then you see eventually much of matter and antimatter would annihilate with each other and disappear, but 2 of them would remain, and that's supposed to be us. So first of all, we should be grateful to a billion friends that they sacrificed their life for us to be living today. But in addition, we need to be thankful for somebody who somehow, at some point, managed to turn 1 out of billion antimatter into matter. Who did that? That is still a huge question in cosmology and particle physics. And one popular idea is called leptogenesis. So if you try to turn antimatter into matter, you immediately run into a problem because let's say matter, electron, has charge negative E, and its antimatter counterpart, its positron, has charge positive E. We know electric charge is conserved, so they can never ever turn a positron into electron. So if you go to the list of matter particles we know and ask the question, what could be done about this? Well, you see a particle named neutrino, which is the form of matter particle and also antimatter, but they don't have electric charge. So if neutrino has charge 0, antineutrino has charge negative 0, which is also same as 0. So that's the only kind of matter particle that can go from matter to antimatter or vice versa. So that's where people came up with this idea that maybe neutrinos did this job to reshuffle matter and antimatter 1 part in a billion so that we could all survive at the end of the day, and that goes back to these people. So it may really be that neutrinos saved us from a complete annihilation. And I'm not a very graphic artist, so I spend a lot of time changing eyes of incredible to new on the emblems. It looks okay, but anyway, so that's the possibility we'd like to explore. Problem, though, is that if you take this idea seriously, we need to study a new type of neutrinos, which are incredibly heavy, up to 10 to the 14, 15 GeV or so on. And if you would like to study such a state in the laboratory, you need to create and build a really big accelerator. And if I use the current state of the technology to build a collider that goes up 10 to 14 GeV, its size will be roughly like this one. So that would require not only international, but presumably interplanetary cooperation to build such an accelerator. So that will be the ultimate future circular collider, right? So that doesn't sound very realistic anytime soon. But there's one piece of physics which is more sensitive to high energy than low energy. Pretty much all experiments we do go from bottom up. But there's one type of experiment that can do top down, that is the gravitational wave. And when you think of this very heavy right-handed neutrino, but still not at the Planck scale, presumably there was yet another symmetry breaking happening at energy scale. And that would lead to the mass of the right-handed neutrino, just like the mass of the electron comes from the Higgs boson filling up the universe. But when you have this kind of symmetry breaking, again, something similar to superconductor can happen. Namely, the magnetic field can be squeezed into flux tubes, as what we see in a superconductor called type 2 superconductor. So universe may have also produced these tubes of magnetic fields at the time of the symmetry breaking up at a very high energy scale. And that kind of tube of magnetic field in universe is what is called cosmic string. That will lead to the emission of gravitational waves that simplifies this network. And that actually turns out to be more if the energy scale is higher, so that you have actually the possibility of observing gravitational wave coming from these flux tubes or magnetic field generated by this cosmic superconductor at incredibly high energies if we can build and go for these next generation space-based missions. So then you will really learn that we are born and we survived thanks to neutrinos, which disappeared very early on in the evolution of the universe. So anyway, to just sum it up, my talk was about the idea that all of these different things, which don't seem to be related to have any relations among each other whatsoever, is actually based on the simple idea of simple concept of spontaneous symmetry breaking. The way a single idea can be applied to so many different things is really what I think is physics is fun. Thank you.
Thank you very much, Hitoshi, for the wonderful talk, very inspirational. Questions? I think we can.
Yeah, turn the lights on.
Thanks for the nice talk. I had a quick question on this symmetry breaking statement that you had. So you said that if the commutator is non-zero, then your number of degrees of freedom will go down. But if it's a commutator, I guess I would have expected that you kind of continuously tune away from zero. Is there some sense in which, but I guess what you're showing is that if it's zero versus if it's some tiny fraction away from zero, it's some very distinct jump. Is there anything physical there, or like what does the value of that commutator mean?
Yeah, that's an excellent question. So if you start turning off this commutator gradually to zero, what would happen is that this first term would start gradually going to zero. But you can also write down a term which is second power in time derivative. And once you actually look at this is second power in time derivative and second power in space derivative. Time derivative is energy.